Today I'm going to go through the 3 steps that you need in order to do all the potential calculations if you have a polyprotic acid to work with and it's a triprotic acid. So let's kind of go through what that means. First of all, if it's a polyprotic acid, you've got multiple protons. So polyprotic acid isn't going to be HA, it's going to be something like H2A or H3A. Probably not likely to have that many more. So what we're going to do is we're going to do a specific acid and a specific concentration so we get specific numbers. So the acid we're going to use is this one, H3ASO4, which is called arsenic acid. So it's an ick acid. And it has 3 Kas. Every time you have one proton, you have a K for that. So the difference between that and, say, your acetic acid is you'll have Ka1, Ka2, Ka3 for this. Acetic acid would have just had Ka1. So let me give you, which is why we usually just write Ka. Ka1 is 2.5 times 10 to the minus 4. Ka2 is 5.6 times 10 to the minus 8. And Ka3 is 3 times 10 to the minus 13. Now, sometimes instead of giving you Kas, they'll give you pKas, which is just the negative log of these numbers. So keep that in mind. Now you can see that this one is the biggest, and this one is the smallest, and it's always going to work that way. Now, the nice thing about inorganic acids like these is that these numbers are nicely separated, which makes what we're about to do work really well. So what we're going to do first of all is just write out the equation to go along with these, and then we'll come back and look at the rice tables. So Ka1, the step that corresponds to this is, think about it, because it's the 1, it's the first proton, and since this is an A, it means acid. So remember, we're going to lose a proton. So if it's Ka2, it's losing the second proton, etc. So let's look at Ka1. Here's the reaction that goes along with it. We start off with the original acid, H3ASO4, and then we have our equilibrium. Here's the first proton lost. So now we have something that has lost one proton, H2ASO4 minus. Okay, everything's going to be aqueous in this. All right, so if we write out Ka1, it just becomes this. It's just H plus times H2ASO4 minus over H3ASO4. All right, that's my first Ka. That's the biggest one. Now, this would be called dihydrogen arsenate, because remember, it's an ick acid, so it comes 8. So it's dihydrogen arsenate. That would be the name of that ion. Then we have the second step, Ka2. We have to start with what was finished with at the end of the first step. So that's this stuff, H2ASO4 minus, we're going to lose a second proton. So notice there's still going to only be one proton here. And then we're going to have HASO4. Now it's going to be 2 minus because we've lost 2 protons. So this is just called the hydrogen arsenate ion because you've only got 1 hydrogen now. Here's my Ka expression. All right. Oops. H2ASO4 minus. See how easy it is to mess that up? You've got to be careful. I only use this stuff. I was looking up there. Okay, so here's my second Ka2. And then we'll have our third step, and that's where we'll end up with the fully naked, I guess, ion where we've lost everything. So starting with this hydrogen arsenate ion, we're going to lose the third proton, and now we're just going to have ASO4 3 minus. Arsenate ion. So here we go, Ka3, that's H plus. Again, go to here, ASO4 3 minus. Move it up a bit. And on the bottom, HASO4 2 minus. Looking there this time. Now, what this is saying, and going back to these numbers up at the top, what we're really doing, the assumption here is that in each one of these steps, we're assuming we're treating them sequentially, and what we're saying is because these numbers are far enough apart that when you have your typical molecule like this, basically if you have a whole bunch of them, say you had 1,000 of them, that what we think about is just one coming off of each of them. So we have just a bunch of these walking around, each with one missing. And then we're saying, say only 1% of them do that. Then of this little lot that actually did lose one, we're going to think about them in this step, and then only an even smaller percentage of them are actually going to go on to lose a second one. And then we bring that down to here, and then of that even smaller percentage of these that have produced these ones, even smaller number of these are actually going to go on and produce these. That's the way it works when you start out with just the original acid. Okay? Funnily enough, it's actually the complete opposite with the salt, but we'll do that another time. All right, so these are our 3 setups, and it looks like it's pretty straightforward. It pretty much is, but there are some interesting shortcuts and things that come up as we go on through. So what I'm going to do now is actually just do it with the whole thing, all the math. All right, what you have to do is think about which ones you would rank, which one you think would have the highest concentration, which one would have the lowest out of all the species listed, plus hydroxide. All right, so we're going to start off. So what we're going to have is, and just make it pretty straightforward, 0.1 molar H3ASO4. We're going to start with that. So we do step 1. So we're going to have H3ASO4, and we're going to have our first dissociation, and we're going to have H2ASO4 minus. Now remember, this is a rice table. There's my R. Now my I. This is 0.1. This is basically 0. Tiny background concentration of 10 to the minus 7. This is 0. We pretend like this has only just gone in the water, and now it's going to start doing something. So we have a 0 over here. So we have a Q of 0. We know it's going forwards. And by the time we get to the end of this setup, you're going to notice, wow, this looks just like when I do Ka1 for a monoprotic weak acid, or just Ka for a monoprotic weak acid. And that's true. That is absolutely true. We'll come back and add something to that in a second. It will look a lot like that. All right, so we have this again. And now we're going to put in the numbers. And we're going to have x squared, because each of these is x, right, over, and then we have not C0, we actually have the number here, so this is going to be 0.1 minus x. And that equals 2.5 times 10 to the minus 4. Uh-oh, this is too big. Remember that simplification we sometimes do, where we say, this x is going to be really small, so we can get rid of it. Well, we can't. This is too big. 10 to the minus 4, by the time you get to that size, it's not worth it. So I will save you all the math and algebra, but basically this is what you're going to end up with after you've done a bit of tidying up. Okay, so you have to wade through the quadratic. So for those of you who like doing quadratics, off you go. And even if you don't, you're going to have to do it for this one. So once you get the whole thing set up, this is what you'll get. You'll get your 2 roots. X is minus 5.1 times 10 to the minus 3. Negative, you write, no, this is not the root you're going to use, because if that's minus, that would make this go up, not down. So this one we know is bad. And the other one we get, so hopefully that one's going to work, we get x equals 4.9 times 10 to the minus 3. So this is the one we're going to use. So at the end of the first step, when we go back, we'll bring down our E line here. What we've got is that E is 0.1 minus x. So 0.1 minus x is 0.095 molar. Okay, we're bringing these all down. This one here is going to be 4.9 times 10 to the minus 3 molar. And this one also is going to be 4.9 times 10 to the minus 3 molar. Now, if they want to know what the concentration of H3ASO4 is, let's write the reaction down up here, H3ASO4. If they want to know what the concentration of that is at equilibrium in this solution, you're done. If they want to know the pH or the H+ concentration, you are basically done. We'll show why in a minute. And if they want to know this one, you are close to done, but you might want to double check. So first of all, if you're asked for just the pH of a polyprotic weak acid, if Ka1 is significantly bigger than Ka2 by several orders of magnitude, this is all you need to do, because you've got H+. So now you can get pH. But what if that's not what they want? What if they want the concentration of, say, this or one of those other species? So step 2, you may have to consider. All right, so let's look at step 2. All right, so we're starting off with, let's get the reaction down, H2ASO4 minus, and now we're going to let it dissociate. Let's make that a little bit neater. Okay, so we're going to have H plus and HASO4 2 minus. Now, this is where it gets different from everything you've done before, although there's a little bit of a parallel with those common ion things you did before with KSP. What we can say is, what are the initial concentrations? It's not going to be something here and zeros here. There was stuff happened already. So if you go up here, all right, here's H plus. It's X, which we actually have. It's the 4.9 times 10 to the minus 3. I'm just writing it in symbol form for now. H2ASO4 minus, that's also X. And this one is 0 because we're pretending once again, this has only just started to happen, so this is 0. So now what am I going to do? I've got X's here. I'm doing it in symbol form just to kind of show you something. Well, the best thing to do with these is actually use other letters. So since this is 0, we know it's going to go forwards. So we're going to say, once again, we're going to lose some. So I'm going to use Y this time. And this is going to be plus Y. This is going to be plus Y as well. So we're going to have X minus Y. We're going to have X plus Y and just Y. All right. Now we write out our Ka2. Ka2, that's going to be H plus HASO4 2 minus over H2ASO4 minus, and that is going to show up like this. So my H plus is X plus Y, this is Y, and this on the bottom is X minus Y. Now hopefully you'll see why I didn't bother to put the actual numbers in, because this equals, if you remember what the actual value was, it was, let's see now, I've got to look at my number here, 5.6. I don't remember these. You don't need to either. You look them up from the data in the question. 5.6 times 10 to the minus 8. This is small enough. So guess what? We don't have to do any more quadratics. But it's a little bit different than before. Whereas before we would have said, well, this is small, so we think that Y is going to be really small, so we're just going to ignore Y. Well, that's true. But if you're doing X minus Y and ignoring Y, well, then you can do X plus Y and ignore Y, can't you? Now you see what happens? Now you've got X times Y over X. So then you can say, well, if I can do that, then I can do this. In which case, look what you get. Y equals Ka2 equals 5.6 times 10 to the minus 8. Now let's put some numbers to that. You can see kind of a bit more of the logic to it. Okay, so let's look at what the E line was here. You know, our H2ASO4 minus and our H plus and our HASO4 2 minus. Okay, so bringing down the E line. This first one is X plus Y. Well, X was 4.9 times 10 to the minus 3. And now we're going to subtract Y from it. Well, Y is 5.6 times 10 to the minus 8. You try that on your calculator. If you subtract this number from this number, you're basically going to get this number. It's going to come down to a matter of more decimal places than 1. So what you're going to see is that this number is ever so slightly smaller than this number here, but not by very much. So it's basically 4.9 times 10 to the minus 3. So let me write that down. It's 4.9 times 10 to the minus 3 minus 5.6 times 10 to the minus 8, i.e. 4.9 times 10 to the minus 3. This one started off as 4.9 times 10 to the minus 3, and we were going to add 5.6 times 10 to the minus 8. Once again, it's basically the same, but notice technically it's a little higher. This one is a little smaller than 4.9 times 10 to the minus 3. So they're very similar, but this one is a tiny bit higher. So the second step adds a few more protons, but unless your Ka2 is really close to your Ka1, it's adding so few. That's why I said earlier, if you just want to know pH, you can stop up here. Because see, that really hasn't changed. You subtracted that, not much different. And now we have the last one. Let's try to do that, so I'm a bit untidy here. All right, so this one started off as 0, and so now this one just becomes 5.6 times 10 to the minus 8. So if you need to know the concentration of this one, you might be starting to notice the pattern now. This one, this is your estimation for it from at the end of step 2. And yes, you guessed it, in step 3, it's going to get modified a bit. But Ka3 is even smaller than Ka2, so it's really not going to get changed that much. So basically, if you want to know this species, you're done. And you might say, well, how many times does this work out? Well, basically, every time your Ka2 is small enough, so it's smaller than 10 to the minus 5. So that happens pretty much every time. So this is a kind of a convenient little math trick that if you remember it, if you think about it, if you do remember all this and how it came about, you don't even have to do the math. That's sneaky, but it's the truth. But if you're not sure, you don't trust yourself, run it through and think about it. You can even just do it in symbol form if you want to save having to write a bunch of stuff out. Okay, so that gives us most of the concentrations. We've already got the H plus concentration pretty reliably now, so we can also get the OH concentration, and you know how to do that, so I'm not going to do that here. Now we have the third step. That's the last part. That's if you have to absolutely know how much of the absolutely completely devoid of proton species we have, because that's all that's left. HASO4 2 minus H plus ASO4 3 minus. Once again, we're bringing stuff down, but it's a bit more complicated than the one up here on step 2. A little bit more complicated, so let's go through it. What we're bringing down now is the H plus, and the value from H plus basically came from, if you remember, let's see if I can do this a little bit. The value for H plus has come almost pretty much from step 1. So it's basically X plus Y, which really is just X. And then if we look at our one here, this is 0. We haven't had a chance to do anything yet. And then over here, this was X minus Y, which again was pretty much the same as X. So this is slightly smaller and this is slightly bigger. So let's go to the next step. See, can we do any other kinds of things? Let me write my ICE thing in here. So I'm not going to use another letter. So I'm going to use Z or Z, depends on where you grew up. And so now we're going to have minus Z plus Z. See, that looks too much like a 2. And there, that's how I make my Z's look like Z's and not 2's. Okay, so now we're going to have X minus Y minus Z, which, as you can guess, is probably basically just X. So you don't really have to do anything there. That's why we said at the end of the second step, you've already proven you didn't need to go that far. So this one you could have gotten from step 1. Now we go to this one. This is going to be X plus Y plus Z, i.e. basically X. So once again, you didn't need to go all the way through to get just that. This is the one we need to get. So this is just going to be that. So now let's look at the expression. Ka2 equals H plus ASO4 3 minus all over HASO4 2 minus, and that equals my last number, which is 3 times 10 to the minus 13. So we're getting really tiny, so this is definitely small enough. So let's have a look about doing the substitutions. You move this so I can get a bit of space. So what are we going to do? What are we going to substitute in? We're going to have, you can write X plus Y plus Z if you like. I'm just going to write X here though. We're going to have X up here. We're going to have Z. And then on the bottom, we're going to have X as well. Now, I do want to caution, because I just realized I should have mentioned this point. I'm actually going to go back and do a slight change on this, because I'm actually going to put the X and Y in there, just to be on the safe side. Just double check that. Why am I doing that? Because there might be just enough of a change in here where I should take a look at it. Okay, so I am going to put the Y in. But I can assure you the Z is going to be really tiny. All right, so quick change. This is approximately X, but I am going to keep this and this when I go down to show up my math, to show you what's going to happen on the second step. Sorry, KA3 step. KA3. So bringing in these numbers. This is going to be X plus Y plus Z times by ASO4, which is Z, over, and then this is going to be X minus Y minus Z. Okay, so what we're basically going to end up with is getting our final concentration here, which is Z. Okay, so your instructor has just proven why you have to be very careful when you're keeping track with all this, because sometimes you can get on a roll too much. So let me show you what I did. Some of you are probably already going, why did you do that? So let me show you what I did. I was happily going along down here, and everything I've done is consistent with my table, but I'm assuming most of you have figured out what the mistake is. If we go up here, here's the mistake, okay? I can't bring down the wrong number, okay? So what did I do? Instead of bringing down this concentration, which is Y, I brought down X minus Y. So I was basically repeating myself from before, which is not what I wanted to do. So let's correct this table. Okay, so this is HASO42 minus. This is the Y value. So what I should have done is, instead of this being X minus Y, this should just be Y. It's not X minus Y. Okay, that was the E from the previous step. So that's what happens sometimes. So this should be Y. There we go. Now I can see. I knew there was something wrong going on over here. So this is Y. This came from the end of step 2. This is the amount of HASO42 minus. Then over here we have H, and that has come all the way from part 1. So this is the X from part 1, the Y from part 2. And now we're going to add on the Z from part 3. And this was 0. So this was what I did wrong. I should have had Y up here because it comes from here, not from the previous step. So let's fix this, shall we? So this shouldn't be X minus Y minus Z. This should just be Y minus Z. Okay? Now, this is why I know something weird was going on here. This shouldn't have canceled like it did in step 2. It is simple, but it's not as simple as that. It's too easy, right? It looked too good to be true. And it usually is in that case. So here we go. Let's do it now. This is going to be X plus Y plus Z, those three pieces. This is going to be my Z. Make sure it looks like a Z. And then this on the bottom here is just Y minus Z. Okay. So let's go into our approximation thing again. Like I said, this is small enough. So we know that Z is so small that if we added or subtracted to X and Y, or X or just Y itself, it's not going to change anything. So I can cross that out. But that's where we stop. So now let's go in and get our values. So this was X plus Y, 4.9 times 10 to the minus 3. And we're going to add on 5.6 times 10 to the minus 8. There it is right there. So this is basically 4.9 times 10 to the minus 3. This is Z, which we're looking for. And then on the bottom, now you see why it's not going to cancel. On the bottom, we have Y. And Y is 5.6 times 10 to the minus 8. So instead of being able to just cancel these two like we could on step 2, we do have to divide them. Well, you know, it's not like that really takes that much work on your calculator, is it? It's not like having to do a quadratic. So there we are. We do that. And once we've done that, excuse the paper noise. Once we've done that, we've made our approximations, we will finally get our number. And what we get is that Z is equal to 3 times, 3.4 times 10 to the minus 18 molar. So that is the concentration of ASO4 3 minus at equilibrium. In other words, it's pretty darn small. It's basically the smallest thing you're going to have. And when you find the OH concentration, we already had the pH concentration from the pH and the concentration of H plus from step 1, the 4.9 times 10 to the minus 3. There it is written there. If you do the math for that, what you'll get for the OH concentration is 2 times 10 to the minus 12. So this is even smaller than the OH concentration, and that isn't particularly high because this is an acidic solution. So the final answer is, if you want to figure out who's present in the most and the least concentrations, we finally got everything figured out. So let's go ahead and figure out who's the highest. Highest? The intact acid. Remember, it's a weak acid. So for all weak acids, the highest concentration is going to be the stuff that's the original intact acid. Now, let's go down a bit. The next highest one will be H+. And the one that's a bit below that will be H2ASO4-. Remember, the first step created equal amounts of these, but then the second step, we made a bit more of this, and then a negligible bit more in the third step, but we lost some of this in step 2. So that's why these two are the next highest. Then we go down even further still, and the one we're going to have even less of is HASO4-, because only some of this lost another proton. And then after that comes OH-, and then absolutely dead last is ASO4-3-. In other words, almost none of them fully lost all 3 of their protons. And this is basically the same kind of pattern we see even in a diprotic, except you won't have as many species, but the one that's fully intact you'll have the most of, then the one that's lost 1 proton, and then the one that's lost both protons. It comes about because Ka1 is bigger than Ka2, which is bigger than Ka3, or Ka1 is bigger than Ka2 if you have a diprotic. The other thing, it's common ion. Every time you make a proton, that messes up the equilibrium on the next step, so it makes it even less likely to go forward. So yes, common ion is at work here. But there's your ranking. And you have the numbers, we did them already. Now if you want to see this written out a lot more neatly, it's also in the lecture notes, but now you've actually seen it grow in front of you. So hopefully now this makes a bit more sense. And don't worry, you won't be expected to know any of these Ks. Just remember that we might give you pKas instead of Kas, but that's about the only thing you would have to do is turn those into Kas.